My thanks for the invitation to give a talk. This recent advances in mathematics and related areas. I really thank Kalyan Chakravarti for the invitation and Pranav for helping with all this uh, lectures and the details. It's a great pleasure. I would have, of course, liked to be at KSOM. It's a really great place to be there. Uh, but anyway, so let me start my talk with this. It's a finiteness theorem for potentially and twist equivalent Galois representations. The work is basically some extensions of Faulting's finiteness criteria, some remarks on that. And it's joint work with Plavan Das, who is at CMI. Yeah. Okay. So let me start with some motivation. So let's X be a smooth projective variety over a number field, and we can take V to be a finite prime. I want to say, what does it mean to say this variety has good reduction? Okay, I think I have to. Yeah, good reduction at a place V. So what? So you look at the completion of K at V, and O will be the ring of V-adic integers in KV. The variety X is said to have good reduction at V. If X has a smooth model, I put it as script XV or OV, and said that the generic fiber of XV is smooth. It's isomorphic to, that is, the generic fiber is XV cross spec KV. So I should have said, and XV is a smooth projective variety over OV. Yeah, so this should have been script XV cross spec KV, and XV is a smooth projective variety. So then you say the variety has good reduction at or at V. And Fontaine showed that there are no abelian varieties over the rationals with everywhere good reduction. Okay. So that means if you are taking the case of elliptic curves, then you would like to say the discriminant polynomial should not have any roots or Q, or rather should be separable all the time. Okay, at all the prime reductions. And it can be seen that if a smooth projective variety curve of C of genus at least one defined over K has good reduction at V, then its Jacobian JC also acquires good reduction at V. So in particular, Fontaine's theorem implies that there are no smooth projective curves of genus at least one over Q, which has everywhere good reduction. So this is a corollary of Fontaine, in particular for elliptic curves, one also knows that, but I'm just saying for any higher genus curves also one knows that there are no higher genus curves or the rationals which has everywhere good reduction. Okay, so, oh my God, I don't know. Okay. Now, in a bid to construct higher genus curves with everywhere good reduction over number fields of small degree, Basses and Vauxhall introduced the notion of twisted good reduction of smooth projective varieties. Okay, a smooth projective variety X defined over a number field K is said to have twisted good reduction at a finite place V if there exists a smooth projective variety X dash defined over K, which has good reduction at V and is a form of X. That means it becomes isomorphic to X over a finite extension L of K. So in other words, it has twisted good reduction if you can find some other variety X dash which becomes isomorphic to this original variety over some finite extension, and this variety X dash is unramified at V. Okay, this is what is this. So the point is that, whether we want to produce curves with everywhere good reduction, but what you can produce over small number fields, quadratic extensions or degree 3 extensions of rationals. What happens? Can you produce curves with everywhere good reduction? Okay, and what Basses and Vauxhall could do is that they could produce curves over degree 4 extensions, which has everywhere good reduction, but over degree 2, they can only produce things which has twisted good reduction everywhere. So they produce infinite family of pairs consisting of a quadratic number field and a curve C of genus 2 curve, such that it has everywhere twisted good reduction. Okay, these curves, of course, as I said, good reduction, everywhere twisted good reduction, but they acquire good reduction over a degree 4 extension of Q, but over quadratic extension, they acquire only twisted good reduction. They also showed The finiteness of isomorphism classes of elliptic curves defined over a number field K with twisted good reduction outside a finite set S of places of K. Okay, so this is also the short, and this, as I said, for good reduction, it is a old result due to Shafarevich, but uh, and that the proof of this later result follows the lines of the original argument due to Shafarevich, and that rests on Ziegel's lemma on transcendence. So our motivation, one of our motivations is to start with this and try to prove it using the theory of L-adic representations. So one of our aims out here is to generalize this finiteness result to the context of L-adic representations. So recall that Shafarevich proved the finiteness of elliptic curves over a number field which has good reduction outside a finite set of places, and Faltings proved the same theorem for abelian varieties. These are the Shafarevich, proving the Shafarevich conjecture. And as a part of the proof, what Faltings did is to prove some finiteness theorems for pure L-adic representations. So we try to consider this theorem of Faltings and try to see how it can be adapted to this setting. And what is the finiteness criteria proved by Faltings? I will explain this theorem again. Is that you given n the dimension, d I suppose it should be, and F is a local field, which is a finite extension of QL, and a finite set S of places of K. So then, so if you are given this data, there exists a fixed finite set T of finite places of K, which is disjoint from S, such that the traces of the Frobenius conjugacy classes at the places belonging to T serves to uniquely determine a continuous semisimple representation from GK to GLDF. So if I take any semisimple representation from GK to GLDF, or whatever, which is unramified outside S, and it's pure of some, just unramified outside S, continuous semisimple representation, then you look at the character of this representation evaluated the Frobenius conjugacy classes at the places V and T. This T is fixed, it doesn't depend on the representation, and this uniquely determines the representation. And from this, assuming a purity hypothesis on the representations, finite results are deduced. I'll come in greater detail to these things. I just want to give an outline for just so now I just want to say that when A is an what to go from good reduction for varieties to L-adic representation. So I recall that there is this theorem of Sayre and Tate, which was extending the work of Neron-Ogg and Shafarevich and Grothendieck also on elliptic curves. This is the existence of Neron models. Showed that an abelian variety A has good reduction at a finite place V of K, if and only if the representation of the absolute Galois group GK of the number field acting on the Tate module VLA attached to A is unramified at V. Okay, so what happens is the good reduction properties of algebraic varieties, of abelian varieties, which one can talk about good reduction from the point of view of existence of a model on the ring of integers, but it can be detected at the level of L-adic representations alone. And that's what this theorem of Sayre-Tate, Neron-Ogg, Shafarevich tells you, right? And unramified at V for all L not equal to characteristic of V. So from the L-adic representation can determine whether a abelian variety has good reduction, right? This is, note that this is not true for curves of genus G. Okay, the implication is only one way, but not both ways. But anyway, I'll not come to that, but I just want to say that this is not a theorem which holds in full generality. Even for curves, it's not there. Okay. And what happens is, so this, if you use this description in terms of L-adic representations, and if you are able to generalize the results of Faltings to the setting, that would allow us to recover the results of Basis and Boxall instead of who proved the theorem using the idea of Shafarevich, but instead we can do it for abelian varieties also. Okay, so now that's a kind of outline. There is still some more I just want to say. So the other motivation, which was kind of related to this. So what happened was in a joint work with Vijay Patankar, so we proved some refined versions of strong multiplicity 1 theorem, and for what is context of potentially equivalent L-adic representations of the absolute Galois group GK, right? So here we are, of course, I should have said we are working with the global field, which is a number field or the function field of a curve over a finite field. Okay. And what we say is two representations of a group are said to be potentially equivalent if they become isomorphic upon restricting to a subgroup of finite index. Okay. And now if I have, suppose rho 1 and rho 2 are two representations of the absolute Galois group, GK to GLTF, and T be a finite set of places of K, the representations are said to be locally potentially equivalent at the set of places T of K if the restrictions, the local restrictions, rho 1 V and rho 2 V to the local Galois groups GKV, where V is a place of K, V is belongs to T, are potentially equivalent at the places V belonging to T. So we are saying that two representations are potentially equivalent if restricting to a subgroup of finite index they become equivalent. And what we are saying is that locally equivalent, meaning you restrict it to the local Galois group, they become potentially equivalent. Okay. Now it can be seen as an application of Chebyshev density theorem that if two continuous semisimple L-adic representations of locally potentially equivalent at a set of places of density 1 and K, then they are potentially equivalent. Again, I will come back to this in more detail later. Now, the refinement consists in weakening the hypothesis of the multiplicity. One theorem. The box has gone up to assuming only sets of positive density, right? Not of density 1, but positive upper density. But we can consider other refinements of the strong multiplicity 1 theorem. For example, there are these analytic forms of the strong multiplicity 1 theorem, say in the working in the context of cuspidal automorphic representations, where you would like to say, works with only finitely many local representations attached to the Archimedean places and finite places. But you take the first set of local components up to some bound, so that the bound on the residue field degree, residue field cardinality, which will depend on the analytic conductors, okay, of the two representations. And then one can say that if the local components at this finite set of places agree for this first set of places together with the Archimedean places, then you can say that the cuspidal representations are isomorphic. So this is a kind of analytic version of the strong multiplicity 1 theorem. But what we are trying to do is to considerations of potential equivalence and this basis Boxall and other things. These observations lead us to consider extending Falting's theorems to the context of potentially equivalent representations. So that's so I just trying to give the motivation for what we are going to look at. I'll come to details now. Again, I just give a brief outline of what I'm going to do this thing. So what we first observe is that in a context, so if you look at potential equivalence for fixed K, N, and F, say actually it should be D instead of N, small n. This is determined by the M trace, okay, chi rho M, where M trace is a function of G going to trace of rho of G to the power M. If M equal to 1, this is the usual character, but M trace function or the M character we could have called it, and attached to a semisimple representation. And it's for some natural number M depending on the parameters involved. Okay, and then what we do is once we have done this in terms of M trace or the M character, we can use Newton identities. We linearize the M trace function in terms of representations, and then we appeal to Falting's method to prove the required generalization. So this is what I'm going to do, and this is the motivation. So let me start with the some of the details. Okay, but before that, I'll start, first recall Falting's finiteness criteria. Again, I'll state the theorem. So what you're looking at is K is a global field, which is either a number field. So let's take it to be a number field. And L is a rational prime, co-prime to the characteristic of K. And S is a finite set of non-Archimedean places of K and containing the places dividing L. This will always be an implicit assumption if I'm not stating it. And F is a non-Archimedean local field of characteristic 0 and residue characteristic L. Again, these are all this. And I fix a natural number D. Okay. So that is the degree of the representation. So then what faulting says is there exists a finite set T of finite places of K, which is disjoint from S, okay, such that the isomorphism class of any continuous semisimple representation rho from GK to GLDF and ramified outside S is uniquely determined by the finite collection trace of the character values evaluated on the Frobenius conjugacy classes, right? That's what one is saying, where rho sigma v denotes the Frobenius conjugacy class corresponding to the place V in rho GK, and trace is the square. So by the character values are the Frobenius conjugacy class. This is what faulting's theorem says. And I also, before I go further, I want to say what's application of faulting's theorem with a stunning application, which is in order to do that, I'll say what is the purity, notion of purity. So we are looking at an algebraic integer alpha in Q bar, and it's said to be a Weyl number of weight W corresponding to a finite field FQ or a non-Archimedean local field with residue field isomorphic to FQ of Q elements. If for any embedding phi from Q bar to C, so you embed the ring of algebraic numbers, the field of algebraic numbers inside the complex numbers, and now you take the usual absolute value on complex numbers. For any such embedding, the absolute value of phi of alpha should be Q to the power W by 2. Okay, where W is the weight of the Weyl number with respect to Q. Okay. Now we say, when do you say a representation rho from GK to GLDF is said to be pure of weight W and degree at most D? So I need two concepts. If at any unramified place V of K, the eigenvalues of the Frobenius conjugacy classes rho sigma V are algebraic integers of weight W, and the degree of this algebraic integer should be at the maximum capital D over Q. Okay, so I need both these things. What faultings will do is, if I'm working with abelian varieties, we'll assume that the characteristic polynomial has integral coefficients, for varieties, in which case the degree, this capital D is just small d, right? But I'm not assuming that right now. But anyway, just this small. Okay, we have the following lemma on the finiteness of the number of Weyl numbers. So fix a finite field FQ. So then there are only finitely many Weyl numbers attached to FQ of degree bounded by D and weight W. Okay, so let's see a proof of this. So the proof is as follows. So let alpha be such a Weyl number. Now the minimal polynomial of alpha over Q is of degree at most D, because that's the assumption that the degree of this minimal polynomial should be at most D, and the roots of Weyl numbers of weight W. Okay, now the coefficients of the symmetric polynomial, because are elementary symmetric polynomials in the roots, and so they are bounded by a function depending on only Q, the degree D and W, right? But they are integers, they're rational integers. But so there are only finitely many such coefficients, hence there are only finitely many such polynomials, and hence finitely many such Weyl numbers. Okay, so I should have said out here that the coefficients are all rational integers, and they are all bounded on, and so there are only finitely many. Okay, so that is a theorem. Then what happens is, so an immediate corollary is the following finiteness statement for pure semisimple L-adic Galois representations. This is faulting's this thing. So you fix natural numbers n, w, and d, and let k be a global field and L be a rational prime, co-prime to the characteristic of k, and S is a finite set of non-Archimedean places, so on, and F is this thing. Then up to conjugation, there are only finitely many continuous semisimple representations rho from GK to GLDF that are unramified outside S and pure of degree D and weight W. Now, why is this a corollary of the previous finiteness criteria? The previous finiteness criteria tells that there are a finite set of places T which determines so that the character values of the Frobenius conjugacy classes determines the representation, but that's a finite set of places. And in each one of those finite set of places, the QV is finite, is well determined, and we have assumed that degree D and W are bounded or given to us. So there are only finitely many Weyl numbers possible at each of those finitely many places. So which means there are only finitely many character values possible. And so everything is finite. Since there are only finitely many character values possible, and this character values determines the representation uniquely, we have got Falting's finiteness theorem. It's a simple corollary of purity plus the finiteness criteria which I had stated earlier. Okay, and what is Falting's uses this to deduce a version of Shafarevich theorem. We already saw Shafarevich theorem in the sense of for the elliptic curves. It's generalized as the Fontaine's theorems on non-existence of elliptic curves with good reduction, but the Shafarevich theorem is to say that there are only finitely many conjecture to Shafarevich finiteness conjecture for abelian varieties, which is to say that if you look at a number field K, you have kept a finite set of primes S. Then what Shafarevich says is that up to isogeny, there are only finitely many abelian varieties which are good good reduction outside S. What Faltings had proved earlier was this Tate's isogeny conjecture, which he had proved earlier, which is this things about the isogeny between abelian varieties are determined by what it does on the Tate module, and from that he got to this Shafarevich conjecture because the L-adic representation determines the isogeny. Anyway, I will not get into this details, but it's well. Okay, so in this note, what our aim is to consider an extension of Falting's theorem to the context of potential equivalence. So first, what we do, we define a weaker notion, as I told earlier, of the notion of equivalence of linear representations. So given a linear representation rho from G to GL, actually it should be GLDF, define its M trace, chi rho M, to be the function G going to trace of rho of GM. And we say that two representations of G are said to be M trace equivalent if their M trace functions coincide. Okay. Now, so we have what's the theorem? So let K be a global field, the same notation, and rho 1 and rho 2. See, of course, we want to determine a representation from its character or M character or the M trace. And it's natural to assume the representations are semi-simple. Continuity is a natural assumption. And we are assuming it's unramified outside a finite set of places. That's not really essential, but it's okay. And then the following, so I just want to state a relationship between potential and M trace equivalent. So then the following are equivalent. So I'm saying that the representations rho 1 and rho 2 are potentially equivalent. That means there is a finite extension L of K, so that the restrictions of rho 1 and rho 2 to GL, the Galois group GL, are equivalent. Second, of course, so 1 implies 2, which is immediate. There exists a set of places T of K of upper density 1 and disjoint from S, such that the local components rho 1 V and rho 2 V are potentially equivalent as representations of GKV. Right? If the representations are globally potentially equivalent, then of course you can work with any place V of K, and then you will always get this, right? But I'm just assuming density 1 is enough, whatever it is, right? I have not defined what's an upper density, but anyway, that's not a, and maybe I would define it sometime soon. So then there exists a positive integer M depending only on D and F, so that at a set of places T disjoint from S of density 1, which are unramified for rho 1 and rho 2, I will say that the trace of the character values on the mth powers are equal. That is, the M trace characters are equal on the Frobenius elements, right? Trace of rho 1 of sigma V power M is equal to trace of rho 2 of sigma V power M. Okay, and oh my God, um, and the fourth, there is also one more condition that which is I would say that this representations are wait, my God, I will immediately find it. Just a minute, sorry. Yeah, so this is a third condition. There is a fourth condition, which is anyway, I think I'll come back to the fourth condition. Immediately, I'm just blanking out. Okay, so the implication 1 implies 2 is obvious. For 2 implies 3, so let me state what is 2 implies 3. 2 is that there is a set of places of upper density 1 so that the local components are all potentially equivalent as Galois representations of GKV. And 3 is to say from local potentially equivalence to say that the trace values for a fixed M are equal, right? Where this M depends only on K and F, right? And it can be assumed that the set of places are unramified having the following holes. So what we are saying is for each V in T, there is some natural number KV, because I'm assuming it's unramified, the inertia does not play a role about potential equivalence. And I know that it depends only on the Frobenius conjugacy classes. Some power of rho 1 sigma V to the power KV and rho 2 sigma V to the power KV are conjugate. The problem out here is that the KVs can vary as V varies, but we want to uniformly bound and say that there is a fixed integer M which does the job. Okay, so to prove 3, we may as well work with the semi-simple part of the Frobenius conjugacy classes, right? You just want to know only the traces, right? So that's enough to work with the Frobenius thing. And the following lemma, so is based on the fact that non-Archimedean local fields have only finitely many roots of unity. So that is the main part. How to go from 2 to 3 is what we do. Suppose if you take G1 and G2 are two semi-simple elements in GLD of F bar, and suppose there exists a non-zero integer K, so that G1 power K and G2 power K are conjugate in GLD power F, in GLDF, then there exists a positive integer M which depends only on F and D, and so that G1 power M and G2 power M are conjugate in GLDF. Okay. And the proof of this lemma, since we are working in GLD, two elements are conjugate in GLD F bar if and only if they are conjugate in GLDF. So that's the thing. It's enough to work with GLD F bar. Now you look at EB, the extension of F in F bar generated by the eigenvalues of G1 and G2. And we see that the degree of E over F is bounded by factorial D. It should not be R factorial D to the power square of the factorial D. So anyway, what this says is that the degree of the local field E over QP is uniformly bounded as G1 and G2 ranges over the elements in GLDF. Okay, and since the number of roots of unity is in a local field is just depends on the degree or the base field QP, QL in this it should be. It follows that the number of roots of unity in E is bounded by some positive integer M0 depending only on F and R. Okay. Now let alpha 1, alpha n and be the eigenvalues. By hypothesis, what we have is up to a permutation, alpha I power k is equal to beta I power k. I have changed the permutation. And here alpha I and beta I differ by root of unity which lies in E. Okay. And just from the above comments for m equal to m0 factorial, we have alpha I power m equal to beta I power m. Okay, actually I should have said alpha I is equal to beta j, but we have this. We have alpha I, it's k, but they differ by root of unity. But this root of unity has a bounded order, and that bounded order is which is given by this m0, and also we can work with some m0 factorial, and then we'll have that alpha I power m equal to beta I power m, and then this will because there is also this roots. The permutations, so it takes care of that. So therefore, both G1M and G2M are conjugate in GLD F bar, and hence they are conjugate in GLD F. Yeah. Anyway, this is basically the theorem. I think it's okay. For the proof of the remaining two implications, I will just recall the following algebraic analogues of Chebotarev density theorem. So, which is I look at an algebraic group defined over local field f of characteristic 0, and I look at a continuous representation unramified outside S. And if I take a closed subscheme, that is, so what this the usual Chebotarev density theorem uh, is, you work with the representation of the Galois group, which is finite, like an Artin representation, finite image, and then you are looking at a collection of conjugacy classes in the group, and then one says that the density of places primes which such that the Frobenius conjugacy classes lies in the given collection of conjugacy classes is just the distribution is a probability distribution, right, with respect to the cardinality of the conjugacy classes. Here, what we are trying to do is we are working with representations which are no longer finite. They are infinite image. And then we would like to state a version of the Chebotarev density theorem. So this was started by Serre in his paper Calc theorem, the application of the theorem, the Chebotarev, and one can just algebraize it. And so the condition is given as follows, that the conjugacy class should be of a particular type. And the point is that the conjugacy class X, this is here, X is the conjugacy class one is working with. It's a closed subscheme. It should be a closed subscheme of this reductive group M. The only reason I'm working with M instead of GLD is at times I would like to work with GLD cross GLD and slightly more generally. So I'm just giving myself the freedom to work with some, which is this. But it's the proof is not the same, right? And so the conjugacy class is of the point, I look at the F points of the conjugacy class XF intersect with the image of the Galois group, right? So X is something which is invariant under conjugation, but it's a closed subvariety. And then you look at the set of conjugacy classes which lands inside this C, which is there, and that has a density ds, which is a rational number, which is just the number of connected components of 0. So 0 is the algebraic monodromy group. So number of connected components of 0 which lands inside X. Okay, so this is what one is saying, where phi is a set of connected components of 0, and psi is the set of those connected components so that the corresponding connected component is contained inside X. So X is a conjugacy condition. So this is exactly if the image of rho is finite, this is exactly Chebotarev density theorem. But this gives the Chebotarev density theorem in the algebraic context when image is no longer finite. It's an L-adic representation, but the conjugacy condition should be given by a closed subvariety, which is invariant under the action of the group, algebraic group. Okay, so this is exactly the theorem which is working. Now, so we are looking at the subset of GLD cross GLD consisting of elements with the same M trace, right? XM, which is G1, G2, which is the trace of G1 M. The set XM is a conjugacy invariant Zariski closed subvariety of GLD cross GLD. And what we have assumed that is by 3, that there is a set of places of density 1. So that, so I'll tell you what the condition 4 is. The condition 4 is that rho 1 and rho 2 are M trace equivalent. Yeah. So what we want to say is condition 3 says that there is a set of primes of density 1 such that the local Frobenius conjugacy classes have equal M trace. Okay. But I would like to say that the equality of the M trace holds for all the elements in the group. In other words, the M characters are equal from this, from going from density 1 to all the things. So now you look at the Zariski closure of the image. So this is where M is the product group, GLD cross GLD in this case. And G0 is the connected component of identity. And the equation 1 is that these elements satisfy the above identity. So what happens is the corresponding pair, rho 1 sigma v, rho 2 sigma v, they belong to this XM, right? and this set of places of density 1. So now by this algebraic Chebyshев theorem, it follows that the entire group, because it's density 1, so all the connected components has to lie inside Xm. That means the entire group has to be sitting inside Xm, which means every element of G satisfies trace of rho 1 of G power m equal to trace of rho 2 of G power m. This is what we obtain. Okay, so this is what we get, that the m trace characters are equivalent or equal from, that is part 4. Now you would like to say that if you know that the m trace characters are equal, then you would like to say that the representations are equivalent, potentially equivalent. So what we do is we go to a subgroup, normal subgroup of finite index in GK, corresponding to a finite extension L of K, and we can assume that rho of GL is contained inside the connected component, G naught of F, the F points of the connected component. But if you take a connected algebraic group, the mth power map is surjective. Okay, and it's a connected algebraic group is surjective, and basically what happens is, and a neighborhood of identity is dense. So what happens is, it follows that for a the nth power map is surjective, and so what you will get is, if you take a neighborhood of identity in the connected component, it is dense, so you will be able to capture a neighborhood of identity for which the character values are equal, chi of rho 1 sigma equal to chi of rho 2 sigma for all sigma in GL. And since the representations are assumed to be semi-simple, it follows that rho 1 is isomorphic to rho 2. So what this theorem says is that potentially equivalent, globally potentially equivalent, is equivalent to saying locally potentially equivalent at a set of places of density 1. But that also is equivalent to saying that some m trace characters are equal for some m which depends only on the dimension D and the local field F. Yeah, that's what is it. So that potential equivalence and m trace equivalents are equivalent. Okay, now I want to come back to the main theorem. We want to extend Falting's criteria to the context of potentially equivalent. So what is the main theorem? So we take a global field L and I fix a local, oh my God, it should be a Q is L power A. Fix also a natural number m greater than or equal to 1, and I'm looking at a finite set of places containing. So sorry, this is not P, it's L. So then there exists a set T of finite places of K disjoint from S with the following property. Suppose rho 1, rho 2 are from GK to GLDF for two continuous semi-simple representations of GK, where F is a non-Archimedean field with residue field of cardinality Q. Anyway, I can work with P also right now, for that, it doesn't matter. Assume that for V not in S, the inertia at V acts by scalar matrices of order dividing M. This is just a general, slightly, the proof gives me this extra assumption I can assume. See, recall that Falting's theorem, he is saying that the representation should be unramified outside S. What I'm going to put in an extra weakening of the hypothesis to say that it need not be unramified outside S, but I would like to ensure that the inertia acts by scalar matrices of order dividing M. Okay, where this M is the same as that M which is there, and that the representations satisfy the following hypothesis: trace of rho 1 sigma V power M equal to trace of rho 2 sigma V power M. Yeah, it's this. So okay, so then I just want to say the conclusion is that the representations rho 1 and rho 2 are potentially equivalent. Okay, so that is, it's gone down. It's unfortunately one can't see it. That's it. Okay, so now I'm going to give a proof of this theorem, and basically how do you get this? So let me first do the, so as I said, what we are trying to do is to work with the Newton identities, but I'm trying to get that. And so this, the reason for doing what I'm going to do now comes from the Newton identities. Okay, so what you do is you look at exterior IV is a exterior vector space, and for any tuple or D tuple of integers R1, R2 to Rd, so you look at the tensor product V of tensor R1, tensor R2, and you can define a degree dr is weighted degree R1 plus 2 R2 plus drd. Okay, and but I'm going to look at this total degree equal to m, right? And what is the dimension? The dimension of uh, is the dimension of the space V of R bar. And the hypothesis that the initial action outside S acts by scalar matrix of order dividing M implies that the associated representation, this the scalar matrices becomes acts trivially because scalar will act by power of M on this vector spaces VR bar. And so then I'm going to look at dm is the dimension 2 times summation of the dimension. So now what I'm going to do, I want to first give a construction of T, how I am going to get T, the finite set of places T, which comes from the Hermite-Minkowski theorem, but let me just say this. So it follows from the finiteness theorem of Hermite-Minkowski. Recall I've defined you what is dm. It's some number which depends on the dimension of V and this M, right? It's some complicated number, which is whatever is there. And I work with all the homogeneous, in this sense, homogeneous tensors of degree M. So I'm varying R bar so that the degree of R bar equal to M. So I'm looking at various such tensor products of exterior powers. This, in some sense, a complete homogeneous. This. Okay. And there are only finitely many extensions L of K that are unramified outside X and degree bounded by Q to the power dm. So dm is twice that degree. Okay. And Lm denote the finite Galois extension of K given by the compositum of these finite extensions. So now I'll appeal to usual Chebetrov and say there is a finite set T of places of K so that the Frobenius conjugacy classes at V of Lm power K corresponding to T, they cover all the conjugacy classes of Galois group. So this is my choice of T. So I've constructed some field extension and I've worked with some finite extension which is whose degree is bounded by dm and which is unramified outside S. Now Hermite-Minkowski says there are only finitely many such extensions, and I take the compositum of these fields, and by Chebetrov I have finite set of places whose conjugacy classes cover this Galois group, finite Galois group. Now comes the next part of Faulting's theorem, which is to use Nakayama's lemma to get at finite generation. Now, suppose if you're given a representation rho of GK acting on V, we consider the associated representation, rho M on VK on VM, which is each of those vector spaces has an associated representation. So I look at VM as a collection of representations of the Galois group on all this VR bar, the direct sum. Okay, suppose rho1 and rho2 are in the as in the hypothesis of the theorem, then let V1 and V2 be the underlying vector spaces on which these representations act. The assumption on the action of inertia outside M, as I said, implies that this rho1 R bar and rho2 R bar are unramified outside S. And just repeating whatever. And let OF be denote the ring of integers of F, and M be the OF submodule generated by N. So you run over all this R bars at the degree of R bar equal to M, that is all those tensor products, and look at endomorphisms of V1 R bar plus endomorphisms of V2 R bar, right? And take the direct sum of such spaces and look at the image of the Galois module and look at the OF submodule generated by that of the Galois group and this. And because the dimension of this subspace of these vector spaces are all at most dm, the rank of OF is at most dm. Okay, if I take the vector space dimension is dm, so the rank of OF is at most dm, which you have. And let MF denote the maximal ideal in OF. Now the quotient, the dimension of the quotient module M mod MF M or the residue field KF is at most dm, because the module M is of rank at most dm. So this dimension of the quotient module is at most dm. Thus the cardinality of the image of the Galois group in this invertible elements is less than Q to the power dm, where Q is the residue characteristic, cardinality of the residue field. Okay, since it is unramified outside S and it's a quotient of the Galois group G of Lm over K, and by the construction of T, the image of the Frobenius conjugacy classes at V in T of the representation of GK on G mod, this thing, they generate the quotient module. Because I told you that the image, when I go down, is going to be a quotient of this group G of LM over K, but this Frobenius conjugacy classes will cover of LM over K will cover all these things. So this image of the Frobenius conjugacy classes, they will generate this module M over Fm. And by Nakayama's lemma, it will follow that the Frobenius conjugacy classes rho 1 M sigma V and rho 2 M sigma V, which we have said it, will generate the module M. These are the representations. Okay, so that's a finite generation which you are getting. Now I would talk about, so this is the finite generation. So for T in this thing, the Frobenius conjugacy classes generate M. Okay, so we have got that they generate the image of the Galois group, the YF module. Now I would like to say how to use a Newton's identity to get the thing. Now Newton's identities allows us to write this M trace. So what is happening is right? As an integral linear combination of the characters chi rho r bar associated to the representation exterior powers of this thing. Remember what our assumption is only on the M traces are equal. Okay. So far I have said this. So for any M, Newton's identities gives you the trace, the power of the on the nth power elements in terms of the elementary symmetric polynomials, and this is where this entire construction is coming in. So this part which is there, this corresponds to, in some sense, V of R bar, the character of V of R bar. Okay, and here we have used the fact that since the dimension is D, the elementary symmetric functions with index greater than D are all 0, but we are working with only the degree of R bar equal to M. Okay, so that's a fixed finite set. Okay, in terms of characters, this yields the following expression for chi rho M. Chi rho of M is minus 1 to the power M times M times some whatever, some number, and minus 1 to the power some. So the point is that these are all integral coefficients, and we'll have chi rho of R bar, which is the character. Okay, sorry. Since a collection of Frobenius conjugacy classes for rho M, they generate the module M. They also generate the image of M in the module of each of these R bar for degree of R bar equal to M. It follows that the character values chi rho R bar are determined by the evaluations of these conjugacy classes. And so the Newton identity expresses the function chi rho M as an integral combination of chi rho R bar. So what happens is, under the assumptions of the theorem, we get that chi rho of the M level characters are equal for all G. What is the assumption of the theorem? That at some finite set of places T, the M row characters at the Frobenius conjugacy classes are equal. But what we are now getting it is for all elements of the Galois group, the M characters are equal. And now the theorem, what we want, is obtained because we know that the proof of the finite generalization of conjugacy classes is now completed by appealing to the equivalence of potential and M trace equivalence. Okay, so this is what allows us to get the theorem. So now let me just give an application. So assuming purity, as in the case of abelian varieties, we can obtain finiteness theorems. And for example, the collection of abelian varieties defined over K and unramified outside S, which become isogenous over collection or a finite extension of K is finite. What Faltings does is we are taking up to isogeny over K itself. That is finite, or you can work with isomorphism classes, but we are assuming that we are given abelian varieties, but we are taking only isogeny over K bar, and that is finite. This is an application of this theorem. Yeah, we could have, of course, assumed that the inertia outside X acts by scalars, but I'm not stating that. Okay, and how does this proof of the theorem follow? This, of course, I indicated orally. So the point is that the isogenies form AB tensor ZL, that is given by the Galois equivariant maps on the Tate modules, so that is so this is the proof of this theorem follows from this, and because we know that the right hand side is determined, by what we have said so far, and so that means the left-hand side, the isogen is also determined. Okay, so now I come back to this applications for twist unramified representations. So I will say that a representation rho of GK to GLDF, a form of rho, recall that Basis and Boxall are talking about forms of some varieties, but now I want to do that in the context of representations, is a continuous representation rho dash, again from GK to GLDF, so that the restrictions of rho and rho dash to GL or isomorphic for some finite extension L of K. And we'll say this representation rho is so that is twist unramified if this representation rho dash is unramified for some place V of K. There is a form rho dash which is unramified at V. Okay, so for twist unramified representations, we have the following theorem. Again, the assumptions are same, and I fixed this thing. Then up to finite order, twisting by finite order characters chi from GK to F star. The only finitely many continuous semi-simple representations. I want to say something. The representations rho are twist unramified outside S, and rho is pure of whatever it is. But we need to put in a condition, which is to say that the connected component of identity of the algebraic monodromy group, so that acts absolutely irreducibly on Fn. Okay, so that's an assumption which is there. So why do I need it? I'll try to give a different proof of what's happening. For that, I will come back to this notion of Dirichlet characters. So we say a Dirichlet character is a finite order character from GK to QL bar star. Okay. Now we can consider a more restricted notion of unramifiedness up to twisting. What we say is a number field is unramified up to twisting by a Dirichlet character. If for each place V not in S, there exists a Dirichlet character chi, so that rho tensor chi is unramified at V. Okay, and we'll say that rho is unramified outside S up to F valued Dirichlet twist if in addition to above the character chi takes values in F star. But that is important, that I want the values to lie in F star. Okay, now a consequence of Hilbert theorem 90 and Schuh's lemma gives a connection between forms and Dirichlet twists. So let me just state that it's a, suppose if you have rho dash or continuous representation of GK to GLDF, and suppose if you have, there is a finite extension L of K, such that the representation of rho and rho dash are absolutely irreducible, and their restrictions of rho to GL are irreducible and isomorphic, then there exists a Dirichlet character chi of GK with values in F star. So what I really want is values in F star, so that rho dash is isomorphic to rho tensor chi. So this is fairly thing, but standard, but I just want to give a proof to say that the values are in F star. The point is that the collection of matrices which conjugate a representation rho dash, rho of GL to rho dash of GL is a torsor for GM defined over F. And by Hilbert theorem 90, we can assume after conjugating my matrix that rho of GL is isomorphic to rho dash of GL. Okay. Now it can be checked that for every sigma in GK, the operator T sigma from rho dash sigma inverse times rho sigma intertwines the representations rho of GL and rho dash of GL. And by Schuh's lemma, T sigma is chi sigma times character, because it's a absolutely irreducible representation. And but since T sigma is in GF, GL and F, this implies that the character takes values in GF, F star, right? So yeah, so it's basically an application of Hilbert theorem 90 together with Schuh that we get this thing. Okay, so the theorem for Dirichlet twists, again, we do the same things. We assume the same numbers, and we fix some natural numbers N, W, and D, and we are saying N, D, and this thing. That rho is pure of weight at most W and degree bounded by D. But what we are going to say is that the representations rho are unramified outside S up to Dirichlet twists. Then there are only finitely many up to potential equivalence. That is what we are saying. Up to potential equivalence, there are only finitely many continuous representations. So the proof of this theorem, I just want to give a slightly different proof of this theorem. So let me just state this. Rho from GK to GLDF is unramified outside S of this thing. Then row tensor UF, because the character value chi takes values in F star, and UF is the number of roots of unity. Chi row tensor UF is unramified outside F. Okay, that is basically because the inertia outside acts by m roots by roots of unity, and the number of roots of unity is UF. So row tensor UF is identified. It's unramified outside S. Now we use a theorem from algebraic groups. If you have a connected algebraic group and you have two representations such that rho 1, some tensor powers are isomorphic, then the representations themselves are isomorphic. And this follows from the representation. It's enough to say that the characters are equal. And for this, you look at the, what you're saying is that the characters, that the tensor powers are equal implies that the characters differ by root of unity. But at an identity element, they are all equal because they are equal at the identity element because the character value is just equal to the dimension and they are the same dimension. And since they differ by root of unity, they will, these characters are equal in some connected neighborhood of identity. There are only finitely many values, so they're equal in some connected neighborhood of identity. But any connected neighborhood of identity in a connected algebraic group is Zariski dense, so the character values are equal everywhere. So that's a proof of this. Assuming the hypothesis, now this theorem, it follows that the representations, I'm just giving you the theorem. Now the row tensor UF for unramified outside S. Now we apply Faulting's theorem directly to conclude that after isomorphism, there are only finitely many representations of the form rho tensor UF for rho satisfying the hypothesis of the theorem. But now we apply this previous theorem. If these are the, so that the UF fold tensor products cover the isomorphism classes of such representations as above. We go to the, so there is some representation rho I. We base change to a field where the rho i's are connected. The algebraic monodromy groups of the algebraic of this rho I tensor rho f are connected, and where n is the n of UF. And then by the proposition above, we see that rho restricted to GL is isomorphic to rho I restricted to GL. So this says that there are only finitely many such representations of this. This gives you another proof of the finiteness theorem for testing by Dirichlet characters. So we could have used a potential equivalence, but I'm just saying we're getting this thing. Okay, I have some few minutes. So I just want to state one theorem before this thing. I probably don't have time to give a proof of this, but let me just state this. It's a slightly curious theorem. So we are looking at isomorphism classes of non-CM elliptic curves E defined over a field K, so that for some quadratic extension L of K, this base change acquires good reduction, right? So this is what we are saying. What we are saying is that there are only finitely many such K isomorphism classes. So there are only finitely many K isomorphism classes of non-CM elliptic curves defined over K, which in some quadratic extension L of K, it acquires good reduction outside up to twist outside SL, outside this primes in SL. I don't have time to go through the proof. I think, but proof uses all these good reduction properties, semi-stable additivity, and it seems to work only for quadratic extensions. So I will just skip the proof of this. Yeah, thanks. Yeah, I finished my.
Thank you, sir, for the nice talk. Is there any questions? Okay. So thank you for the nice talk. Is there any questions? So there is no questions in the seminar hall. Maybe YouTube channel. Anu, is there any question in the YouTube channel?
Accurate, sir. There are no questions in the YouTube channel.
Okay. Let us thanks to the speaker once again.
Okay.
Thank you, sir, for the nice talk.
Okay. Thank you.